but otherwise, Steffi, you can continue letting people in, right? Then I can just
I can do
start
that.
by welcoming everyone in the room already. Thank you for joining us again this week for the Landscape Lives seminar series. And my name is Vivi Petersen, and I'm chairing the seminar today. And then for moderating the discussion afterwards, we have as well Steffi Tofelde. Yeah, and we see many participants and more people coming in, so that's great. And today we're lucky to have Dirk Scherler from the DFZ in Potsdam to give a talk. And Dirk, he did his PhD at Potsdam University.
You're muted.
Yes, I'm back. I don't know what happened.
Sorry, that was me while letting people in. Somebody did it at the same time, and then I unmuted you. Sorry.
Okay, because I thought I was the one in control, but great. Okay, but so Dirk, he finished his PhD in 2010, and then he continued with a postdoc at Potsdam before going to Caltech for a few years. And now since 2014, he's been back at DFZ in Potsdam and also at the Freie University in Berlin. And Dirk, you are a junior professor still?
Yes.
Yes, all right. I wasn't sure if you had been promoted recently. Okay, we don't have to stay on that topic because now we can move on, and I'll introduce your talk for today with the title Eroding the Garhwal Himalayas, Deciphering Climatic and Tectonic Controls with Cosmogenic Nuclides. And as always, after Dirk's talk, you're welcome to ask questions and add comments in the chat that we will open in the end of the talk. And you can also raise your hand, and then we can ask you to turn on your microphone. So with that, I will simply give the word to you, Dirk. And your slides are ready. Yeah.
Yeah, thank you very much. Let me try to close this bar up there. I hope you see everything nicely without something covering things or so.
Yes, we see everything.
Okay, perfect. Well, yeah, thanks first of all for inviting me. It's a great honor to be here. And ever since this seminar series started, I've been really enjoying watching it either live in presence or online. And so being able to watch a recorded talk is also something I think that is very useful, but also makes it kind of exciting because it remains in the web. Anyway, before I start, I also want to highlight the people that I've been working with, specifically on the stuff that I'll be showing during the second half of the talk here, or roughly second half. And that's Sanjay Kumar Mandal, who was a postdoc with us at GFZ, and he's now back in India as an assistant professor. And then PhD student René Kapanush, as well as my colleague Hella Wittmann at GFZ, who's running our cosmogenic nuclides lab, and Georgina King at now University of Lausanne, who was in charge for some luminescence dating that will be presented later. And obviously, there are also a bunch of colleagues that are not able to fit on the screen, where discussing things and sharing thoughts has helped me in developing ideas together with students and postdocs, and I'm very grateful for that. Now, first, I want to switch to this laser pointer thing so I can point at things. Great. Start. Okay, first a note on what follows. And I will be talking a lot about erosion and how that may be linked to climate and tectonics. And the data I'm showing is something that we, as several people and me, obtained. These are observations that usually cover long time scales, so thousands to millions of years. And because I'm aware that this is going to be in the web and people will be watching it that may be not so familiar, I want to just mention that these findings and conclusions should not be confused with the effects that anthropogenic warming together with human land use may have on erosion at present and in the future. So I'm not making any political statements about climate change and whatnot, just to make sure this talk is not going to get abused by someone. Okay, so I don't want to spend too many slides actually on introducing the relevance of the topic, but I chose this figure here is taken from a paper by Willett and others that was following a Penrose conference and published in 2006, and that shows the links or processes that are linking tectonics, climate, and erosion. And there are many arrows with many different terms on it, and I don't want to go through all of them. But in this triplet, so within this realm of these three words, there are a couple of things that also apply to the Himalaya quite prominently. And I'm starting here. As you know, it's tectonics that has created the mountain belt, the Himalayas, but also Tibetan plateau. And it's long been known that this influences atmospheric circulation and creates a strong orographic rainfall barrier along the Himalaya. And not only locally or regionally, but also globally. So it has an effect, tectonics has an effect on climate. Climate itself, we know it has an effect on erosion, and specifically the quaternary glacial cycles, for example, is an example of where climate has changed and is changing basically, and affects erosion rates. Now, the question of where we erode how much, so the focus of erosion within a mountain belt might itself again play back into tectonics in the way that it changes the localization of deformation or other things. Also, erosion, the transporting sediment eroded off the Himalaya out of the system and dumping it into the ocean may affect the global carbon cycle. And this may be a link back into climate. So there are these multiple links between these different, tectonics, erosion, and climate, these different systems, and all of them have been quite prominently studied in the Himalayas. Why? Probably the first reason is because the Himalayas are a pretty wet place, and that's true for most of India, but the Himalaya stands out. And this is a map by Bode Borghagen and Doug Burbank, published in 2006. Based on TRMM satellite observed rainfall rates. And what we see is that there are a lot of places that receive several meters of rainfall, and they basically outline the Himalaya, the strike of the Himalaya. So a lot of rain followed by vast dryness here on the Tibetan plateau. And that has motivated people to link precipitation, specifically monsoonal precipitation, to how the Himalaya works tectonically. There was an early study by Chris Beaumont and others that investigated this link. Others were thinking more about how changes in precipitation through time may have driven the exhumation rates in the Himalaya over millions of years. And then, there are also, of course, different opinions on that. There's a study by Doug Burbank where they looked at present-day erosion or present-day precipitation patterns and proxies for erosion, and they don't always match up, allowing us to think more about the timescales and how precipitation or generally climate might have changed in the past. And then, of course, there's also the topic of transporting not only sediment, but particulate organic matter off the mountain belt and into the ocean, and how that influences the global carbon cycle. And last not least, there are a bunch of other studies that are more concerned about how climate erosion is linked on a global scale, and how the climate change over the last, let's say, 20 million years or so, how that is linked to mountain building and erosion and silicate weathering, stuff like that. And I don't want to go into each individual studies here, but this has been a debate ongoing since approximately 30 years, I would say. And in many of these studies, the Himalaya play an important role simply because they are large, there's a lot of rain, and there's a lot of uplift and erosion. And that basically leads me to a couple of science questions that we can ask. And I'm just listing three here. And the first one is, what controls the magnitude and distribution of erosion in a mountain belt? The second, so the spatial pattern, basically. The second is, how do erosion rates vary along with climatic changes? And is it all about precipitation? Really, like more precipitation, more erosion, less and less. And then over long time scales, how stable or variable are erosion rates in the Himalaya? And I try to get closer to some of the answers to these questions in the remaining, I don't know, 45 minutes or so. Okay, so in the following, I will first spend a few slides on introducing cosmogenic nuclides because they're important for this talk and not everyone in the audience may be equally familiar. Second, I'll be talking a brief introduction into the Gawal Himalaya, which is in the western part of the Himalaya, part of India. And then I'm going to address these three points connected to the questions I was just introducing and argue for a tectonic control, a dominant tectonic control on present-day erosion rates. Then we will have a glance at late Pleistocene erosion rates. And finally, and I'm probably going to spend most of the time of this talk then talking about recently published, somewhat less than 6 million year record of paleo-erosion rates from the foreland basin. And that's probably the most sort of like, for me at least, at present, the most exciting work in which the person I mentioned earlier, Sanjay Kumar Mandal, has played a very important role. A word on terminology, because that might be interesting and some people may take that more serious than I should do. Erosion is the removal of material from the Earth's surface, usually by physical processes, whereas weathering, it's the removal of material by chemical dissolution. And we often use the term denudation to take those two together, it's erosion and weathering. And this is actually what we measure with cosmogenic nuclides. But sometimes, and indeed, blame on me, most often I use erosion and denudation synonymously, and that should not be done. But I will just go ahead in order to focus on the science that I want to tell you. So, cosmogenic nuclides. Cosmogenic nuclides are rare isotopes that are formed both in the atmosphere and in Earth's surface, or in minerals, within minerals close to the Earth's surface, by the interaction with cosmic rays. And cosmic rays are basically particles coming from out of space with high kinetic energy, and they bombard the Earth and the molecules in the atmosphere that create a shower of secondary cosmic rays that rains down, and some of these particles interact with the surface of the Earth. I will be focusing only on cosmogenic nuclide produced within minerals. So this is what we call in situ produced, but I will not use that term throughout the rest of the talk to make it easier. So only talking about in situ produced cosmogenic nuclides here. There are a bunch of nuclides that are commonly used, and each of them has their sort of like advantage and different half-lives. Some of them are stable, like 3 helium or neon. There are those with short half-lives like 14C, and then those with rather long half-lives like 10 beryllium. Production rates are typically very, very low, and SLHL means the production rate at sea level, high latitude, and production rates increase in elevation, but they decrease with geomagnetic latitudes towards the equator. So as we go closer to the equator, they decrease. So production rates are low. Note these are atoms per gram per year. So oftentimes we're just dealing with a couple of thousands of atoms or tens of thousands of atoms in a gram of quartz. And for that reason, we require an accelerator mass spectrometer to measure these quantities. Beryllium is found or is formed in quartz and is the one that I will be using only today, I think. Yeah, I think so. Oh, and for those that would like to learn more about cosmogenic nuclides, I can highly recommend this issue of Relevance, which is dedicated to cosmogenic nuclides. It appeared 7 years ago now, but it provides a good overview of the different applications and principles of cosmogenic nuclides. So check it out. We use cosmogenic nuclides in geosciences or geomorphology mostly in 2 ways. And the first one is to obtain exposure ages. It's quite simple in a way. The cosmic rays interact with our rocks, and in these rocks and the minerals, we have cosmogenic nuclides produced at a known rate. So we know the production rate of these cosmogenic nuclides. We go to the field, collect a sample, and measure the concentration. When we have the concentration and we know the production rate, we can determine the age of the exposure to cosmic rays. assuming that there were no, or that there are no cosmogenic nuclides from prior to the exposure that we are interested in. So you can imagine if it gets more complicated, then we have to make some assumptions or this or that, or clever sampling, which is in most cases the best idea, in order to make sure that we can use these equations and don't run into some issues or biases or something. Note also that this equation neglects radioactive decay, and it gets a little bit more complicated when we include that, but just for simplicity, I'm not showing it here. And the second application is erosion rates. And it's based on a similar, in a similar way, based on the idea that as rocks are very deep below the ground, they don't see any cosmic rays, because the production rate, it decreases rapidly with depth. So at a few meters depth beneath the surface, the production rate is tiny. And as the rock is moving closer to the Earth's surface, because the Earth's surface is eroded and removed, during this travel or this passage, it acquires a concentration. And the concentration, when it arrives at the surface, is higher if the travel time took long, right? If it took long going up, then it acquired a high concentration. But if it moved up very quickly, meaning a high erosion rate, then the concentration is low. And so again, when we know the production rate, some constants that we require, and measure the concentration, again, neglecting radioactive decay here, then we can get an estimate of the erosion rate. And this is basically the principle. And what I've sketched here is a parcel of rock and a surface. But you can also imagine that you have a catchment where there are thousands of rocks or quartz grains or billions of quartz grains traveling up to the surface, and they each acquire a certain concentration. And then the river collects all these sediments and transports them. So we can also go to a river, collect a sediment sample, measure the average concentration in that sample, and then we get an average erosion rate of that catchment. Moreover, if the sediment has been deposited somewhere in the past, we can equally use the sediment, for example, within a terrace or even within a foreland basin, measure the concentration and get an idea about the erosion rate at the time that the river deposited the sediment in a terrace or a valley fill or in a foreland basin. And this is the basic method that we've been applying in the Gawal Himalaya for some time now, and the results that I want to share with you. Okay, so let's move over to the Gawal Himalaya. This Google Earth oblique view on this part of the planet shows India that is moving towards Eurasia at a speed of about 4 centimeters per year. And half of this convergence is accommodated by shortening in the Himalaya. And the rest is distributed over deformation in the Tibetan Plateau and the Tian Shan. And here in the western part of the Himalaya, there's the Gawal Himalaya. It's part of India. And it's also close, interesting note, close to the watershed between the Ganges drainage system that sheds sediments into the Bay of Bengal and the Indus drainage system that transports sediment towards the Arabian Sea. When we zoom into the western Gawal Himalaya, we see this again, an oblique view, Tibetan Plateau in the back, and then we see the high Himalayas with mountain peaks of several kilometers elevation. In this part, not as high as in central Nepal, so it's mostly 6-7 kilometers in elevation, and not 8 like in central Nepal for some of the peaks. This is the Yamuna River that later flows through New Delhi, and this is basically the catchments that I'll be focusing most on in the first part of this talk. And the Yamuna itself continues as the Yamuna here, and then there's the Tons River, continues up here, and this is the Pava River. And the Yamuna has been or is depositing sediments here in the Indo-Gangetic plain, so in the foreland basin. And part of these foreland basin deposits are now incorporated and uplifted and incorporated into the orogenic wedge. And these uplifted foreland basin sediments, they're called the shivalics. And this is where Sanjay went for sampling for paleo-erosion rates over long timescales. Morphologically, we can distinguish here the part that is mostly green, which is the lesser Himalaya. And then those parts here where we see snow and ice, that's the high or greater Himalaya. So the high elevations here, the somewhat lower elevations down there. A brief glance at the geology and at rainfall. The geology, I don't want to go into too much details here, but it's also kind of subdivided. It follows this distinction between the lesser Himalaya and the high Himalaya, in the sense that we have lesser Himalayan sequence rocks in the lower part and then high Himalayan sequence rocks in the upper part. High Himalaya, it's mostly crystalline rocks. So comprises of granites, gneisses, as well as paragneisses and migmatites and whatnot. And then the lesser Himalaya, mostly these orange rocks are meta-sedimentary rocks, so weakly metamorphosed compared to those higher up. But in the upper part of the lesser Himalayan sequence, there are also a couple of granites and granites and gneisses, so more highly metamorphosed. Good, and this is the fallen basin sediment, and up here is the Tethyan sequence, weakly metamorphosed to non-metamorphosed sedimentary rocks that comprise basically the marine rocks of the Tethyan basin. Now on the right-hand side, you see again rainfall as observed by the TRMM satellite and processed for the time period 98 to 2009. So but only about 11 years, but still gives a good impression by Bodo Bokagan. And what we see, don't want to go into the details here again, but we see mostly wet conditions with more than 1 meter of rainfall per year. What is also observed, and even better when you look at the entire Himalaya, is that there is a peak of rainfall here in the greater Himalaya and one here in the lesser Himalaya, at the front of the lesser Himalaya. In Nepal, this would be the Mahabharat range or something. And these are basically, and even the Shivaliks here, you see a little bit of a peak, and all of these bands are due to orographic forcing. So the wet parcel of air is forced into the air and then rains out. Yeah, but generally wet, we can say. Some field photos to get an impression. Here in the lesser Himalaya 1 and 2, it's mostly green. It's relatively steep though, nevertheless, but we also observe, especially in the more interior part, a lot of sediments adjacent to the river. So there's a lot of evidence for an older valley fill that is still preserved in the form of terraces. Then when we go to high elevations, here 3 and 4, this is where it becomes really steep. We lose vegetation, a lot of evidence for rockfall and whatnot. And then at high elevations, there's snow and evidence for ice cover, depending on where you are in the Himalaya, more or less evidence for ice. Okay, brief idea about what the landscape looks like. Now I want to come to present to you some results. And these are results, Temporal-derived erosion rates based on samples collected from these medium-sized tributary catchments along the main rivers here. So again, the Yamuna, Tons, and Paba. And these numbers, these colors correspond to the numbers shown here. And basically, what you see is that most of the catchments in the lower part here have erosion rates that are generally below 0.5 millimeters per year in the lesser Himalaya. And then as we go to the high Himalaya, we get rates that are higher than 1 and even higher than 2 in some cases. This is the general pattern that we observe. There are a couple of deviations here and there, which I wouldn't take too serious or wouldn't be too concerned about. But the overall picture, when plotted against a swath profile that I put across in this direction, I hope you can all see my laser pointer sweeping across the figure. Then this would be the trend of the swath profiles. We see the low erosion rates here in the lesser Himalaya, and then the higher erosion rates in the greater or high Himalaya. Sorry. This is actually work that I've been doing during my PhD and published afterwards. And here's the topography along this profile. Low elevations here, high elevations there. I think this is min, max, and then medium plus minus standard deviation or so. And this here is an idea of, is a guess of the trace of the Main Himalayan Thrust Fault at depth. And this is, maybe I should have added that as a reference here, from a paper by Caldwell, EPSL, I think 2011 or 12 or something, where they use geophysical techniques to image the trace of the MHT at depth. And it's a little bit more to the east from here, so not exactly here, but one important aspect is that, or one important observation from their study is that where the MHT is relatively flat, this is where the topography is low, subdued, and where it gets steeper, this is basically where we see the high Himalaya popping up. So high mountains above the steep part. And if we project it basically over into our area here, it seems to follow the same pattern or the same trend, but it only extends to somewhere there. In the frontal part, there's seismic imaging from the Shiwaliks and the Fallen Basin fill that gives us some idea, but then there's also a little bit of a gap in between. And so main conclusion from that study was actually that if we think that the crust here or the lithosphere is isostatically compensated, and that any convergence related thickening of the crust is compensated by erosion rate, then we would, knowing the shortening rate across these structures, would predict an erosion rate that is equal to where you have these red squares or red rectangles. And that roughly aligns with what we observe. So relatively low here and then higher there. The somewhat increase there might be related to some steepening here, but it could also be related, one thing that I thought about after the publication of this, could also be related to some remnant activity on the MBT, I think. But this is an interesting question, I guess. Okay. So the main conclusion is that there is a strong tectonic control on Holocene erosion rates, that what we measure with 10 beryllium in this case. So we're extending back over several hundreds to a few thousands of years of integration. And it does not really correlate with rainfall. Remember, high rainfall here, yes, high erosion rates, but high rainfall here too, where we don't see high erosion rates, but relatively low. But it does correlate with the geometry of the Main Himalayan Thrust Fault. And I've cited also here Vincent Godard et al. Paper that was published the same year in Geology, who arrived at a similar conclusion. This is also supported by study by Lavey and Avouac in 2001, so quite a long time ago already, where they looked at river profiles across Nepal and calibrated fluvial incision law with the geometry of these profiles and then some other parameters and constants, and basically came up with the pattern of incision across the mountain belt and in Nepal that peaks here, right? And this is exactly where the ramp in the MHT is located, and where we also see some microseismicity ongoing in this area. In contrast, where the lesser Himalaya, where the MHT is relatively flat, we have low erosion rates. And then they shoot up again here in the Shiwaliks, because the MFT makes it, the MHT, the Main Himalayan Thrust Fault, makes it to the surface and thereby gets the name MFT, Main Frontal Thrust. And this is where then the rocks are shooting out with several millimeters per year, as we also know from Lavey and Avouac's work in 2000, I think. So quite consistent. I want to come back to this one here, because one thing that bothered me always when looking at this data is that this is a very high erosion rate, and it's not entirely clear how much we can trust rates this high, because the concentrations are really low. And I was always concerned in these very, very steep catchments that it may also be related to maybe landslides or something, as we don't have multiple samples from multiple years or several catchments of equal steepness or something. I remain sort of curious. Also, all of the other catchments here that have lower rates are typically previously glaciated, which brings along its own complications. But more on that a little later. Now, this is where I make some shameless self-promotion for a paper recently published in JGR Earth Surface, where we looked at a glacier something 50 kilometers to the northwest of here, so not far. And we collected samples along the medial moraine to get an idea about erosion rates that are coming off these steep bedrock hill slopes. And what we see, what we gain, so what we observe from these rates or from these data samples is that we get something like 1 to 2 millimeter per year slope perpendicular erosion rates. Just something specific to this study that we are looking at something slope perpendicular. If we translate that into something vertical and take into account that slopes are typically very steep in these places, then we get something like 1.6 to 4 millimeters per year. So somewhere within this range. And yeah, when I was going through this talk earlier, I was asking myself, what does it really mean? And I'm not entirely sure, but, but it means that we get erosion rates in these catchments or these kind of environments now using such techniques, and they confirm to be high, if that's something to be interested in. Anyway, let me continue, because I see time is not stopping. This is a field photograph again from the Yamuna River, which flows down here in this direction. And there's a tributary coming in. And for those interested in the area, it's Lakamandal. There's a Hindu temple up here somewhere. And we observe a valley fill. And this valley fill is nicely exposed here by road cut. And so one thing I also did during my PhD was to collect samples from these outcrops. And not only here at Lakamandal, but also along the other rivers, so the Tons River and the Paba River and different places. And I also collected a sediment sample from the stream to be able to compare what the erosion rate was back then and now, right? So to have a one-to-one comparison. I also tried to collect samples for dating these deposits or the age. And that was the part that didn't really work out very well. These yellow bars remind me that I wanted to mention that this is a very pronounced top valley fill. And this can be traced all across the landscape, not the landscape, all along the rivers, these three rivers that I earlier mentioned, Paba, Tons, Yamuna. And so it must have been a pretty regional thing filling up the valley. And in most parts, the river has not yet incised, or the rivers have not yet incised down through the entire package, down to the bedrock again. And here's the one figure that I want to show from this paper in 2015, where we compare the recent erosion rate, so referring to a sample collected from the river, and the late Pleistocene erosion rate, samples collected from these valley fills, not really knowing at what time they were deposited. We have a vague idea that it was likely older than 10,000 because we have some exposure ages from the top valley fill, and we have some C14 and some luminescence ages, but these are all very complicated. This happens. So for those of you that reach frustrating points in their PhD, don't worry. Anyway, so this is why there's a bunch of data points for each sample, assuming different depositional ages, and then some other, snow lines that may have varied and so on. But, irrespective of these uncertainties, it turns out that most of these samples indicate paleo-erosion rates were higher during the late Pleistocene, somewhat. That was the main takeaway, which is not very satisfying, I should say. So one of the first things that I did when starting at GFZ was to write a proposal, and it got funded, luckily. And then PhD student René Kapanush, we went back to the field. We went back together. I spent there a couple of days and he spent there weeks. But we selected both this terrace to be examined in great detail. And it's an interesting terrace because maybe just one more beautiful impression of the terrace. It's quite high. It's 130 meters or so. And an interesting thing is that there is a road that goes up here and then comes in our figure again up here and then continues. So there are opportunities to sample this terrace at multiple places, specifically at road cuts. And this is an important thing that I forgot to mention earlier, that road cuts offer the opportunity to get shielded samples, at least samples that were shielded by several meters of sediments overlying them over most of the time that the terrace was, when it was incised by the river again. The interesting thing about this terrace is that the upstream area, so the area where the sediment is collected from that is deposited there, is first of all steep. So it's in quite steep area specifically here. This was the part where I measured something like 4 or 5 millimeters per year erosion rate, but much lower already down here. So this is where actually the ramp is. So somewhere in this area here is the ramp in the MHT, and this is the Lesser Himalaya where there's the flat. It is mostly ice-free. So presently, mostly ice-free, although there are signs of glaciation in the past. And this is something that I also come back to later. The Tones River, Tones Valley, the Upper Tones has been glaciated more extensively. And I've also published a paper during my PhD where we dated moraines here in order to reconstruct the extent of the ice there. What makes this catchment again interesting, I'm losing track of the argument that I want to bring, is that it is mostly crystalline rocks up here and mostly Lesser Himalayan weakly metamorphosed, not weakly, but quartzites down here. So unique lithologies, quartz bearing, which makes it good for beryllium. And you can distinguish the ones that are coming from high up and the ones that are coming from lower parts. Remember, lower parts, lower erosion rates because of Lesser Himalaya and so on. And then here, high erosion rates, high uplift rates. And this distinction he took advantage of. So he went up the road, collected samples from numerous places, a number of sediment samples, and then also a bed load sample from the river, a couple of samples for luminescence dating. In this case, Georgina King did very skillfully infrared stimulated luminescence. And we obtained ages, depositional ages of this valley fill that ranged between 30 and 15,000 years, roughly. In agreement, at least the exposure ages in agreement with what I obtained earlier, and telling us that the fill that we are looking at was deposited over a time scale of about 15,000 years. Extending over the latest Pleistocene, so LGM, globally LGM, not Himalayan LGM, but that's a different story, but still, so we should be concerned about ice glaciers. And the other thing that I want to mention is that the sediment samples, he separated into sand and pebbles, and the pebbles to a size that he could identify those that are quartzite and those that are crystalline, so basically composite of different minerals. And so he could identify the source area to be only crystalline and those only quartzite rocks, and look at the samples individually. But I'll come to that in a second. The realization that this was deposited during glacial times made us think maybe we should try to take this into account. Why? Because it's important for production rates. Remember that if we want to calculate erosion rates from concentrations, we need production rates. Production rates under the ice are close to zero. So this is why it's relevant to take ice into account if it extends some, aerial coverage. So what we did was to use a numerical ice flow model and model the glaciers here in the Tones Valley, but extend the area also over the domain here in the upper Yamuna River, assuming that climate was similar enough so that we could do this. And when we did so, grow these glaciers down to different elevations that we could reconstruct from the work that I had done earlier here in the Upper Tones Valley, we could also see that there is quite some ice, especially in this part of the Yamuna River, and this is also something that we see here in the DEM or in Google Earth, if you take that, or even in the river in the longitudinal profile. So there is a slide of an over deepening, if you want, or not over deepening, but at least there's a kink in the profile that might be indication of glaciation. And I would now probably remove the question mark, but anyway. And I haven't shown you the erosion rates yet, but if you take the average erosion rate that we obtain from the terrace samples and compare it to the modern erosion rate that is shown down here and apply this ice cover correction, then what we see is the larger the ice gets, the more we get the paleo erosion rate down, and we're getting really close to the present day erosion rate when taking ice coverage into account. Okay. So something that is also shown here, but a little bit more complicated, I guess. No ice cover correction, ice cover correction. And the gray bar is the present day erosion rate. And then the hollow samples here are based on sand, and sand comprises material from all rocks in the catchment. And we see that the sand samples are generally higher, they yield higher erosion rates, even though sometimes overlapping with that. And then there are the crystalline pebbles that indicate much higher erosion rates. Interestingly, the quartzite pebbles, because the glaciers never extend into those areas where we have quartzites, they remain the same. There's no real ice cover correction, or only a tiny bit, if at all. But they are almost the same as the present day erosion rate, which was the first surprising finding, to me at least. In addition, if we apply the ice cover correction, and René did a great job because in the field he also made pebble counts in order to quantify how much in a certain way he took his samples, how much crystalline and quartzite pebbles are in there, and also taking into account all the other lithologies that that belong to the high and the lesser Himalayan sequences, and then applied those numbers to correct the sand, then the sand erosion rates also collapsed with the modern erosion rates. Great. So basically, sand pebble erosion rates are similar to modern erosion rates when we correct for ice cover. Quartzite pebbles are similar to modern erosion rates because we don't have to correct for ice cover. It doesn't change with or without correction. Only the crystalline pebbles are higher, even with ice cover correction. And we think that this is probably because they're coming still from, there might be more erosion rate in the past during that time, which is one possibility. It could be also that, this ice cover correction is relatively simple. So I'm not claiming here that we get a perfect correction done, but it all tells me that if anything, then probably those places that were glaciated and really cold had higher erosion rates, whereas those places where we didn't see any glaciation, where it's not really cold and so on, that those might actually not be, didn't change much in erosion during the late Pleistocene. Okay, so these were the conclusions from our paper in 2015, and this one from 5 years later. I think, some of these conclusions probably are now, more questionable, but we also tried to figure out, because the samples were different. They were collected farther down, they integrate over larger areas, and we don't know, everything about the entire landscape. In René's work, we only looked at this particular site there. So it's hard to judge whether all the others, a correction would equally, make them go much down. We tried to do some, playing around with numbers and see what happens, but not entirely sure. Okay, so I've been talking a lot around already, and I don't want to waste any more seconds, but come to the last chapter, which is the statement that is also part of the abstract, is that we think tectonic accretion in the Himalaya controls some erosional cyclicity that you observe in the fallen basin record obtained by Sanjay. Okay, so again, now we look at the Shivaliks here. I'm going through some of the slides perhaps a little bit quicker now to not stress time too much. And sorry for talking so fast. That's probably also related to taking a look at my time, my watch once in a while, and also now taking a sip of water. Rhetoric break. Okay, so here we're looking at the Dehradun Valley, which is this one here, and Yamuna comes out here and breaks through the Shivaliks in this place. Paonta Sahib is nearby, and then there is the prominent Mohand anticline and the Danaura anticline. And there are two dated sections, dated by paleo-Meg in the past, and those sections is where Sanjay went to and collected a lot of samples. Here are two cross sections to give you an idea about what made these sections come up and why they are now exposed. It's basically the MHT coming from here and then makes it to the surface as the MFT, the main frontal thrust. Similar here, only that the level of exposure is a little bit different compared to the Mohan anticline, but there's also another important aspect that makes these two things different, what I'm going to come to in a second. So the first paper he published in Tectonics was about provenance, and he used different geochemical methods as well as circumdating in order to tell apart the source areas and how they changed through time. And the bottom line is they didn't change that much in the end over the course of time that we're looking at. And so the main, I'd say, conclusions drawn from this, that the Haripur Cold section, the one on the left-hand side here, carries mostly Yamuna deposits. And we envision this location to look like this in the past, with the mega fans. And then the Mohan section probably carries sediments from both Yamuna and Ganges. The Ganges is here, remember. Yamuna is there, and this is the Mohan. So when the Ganges and Yamuna rivers sweep across their fans, it's likely that they might influence this. Sanjay also measured, flow directions and all kinds of things. Very thorough work, and it's worth looking at. The other important thing is that the Lesser Himalayan duplex has been active probably since at least 10 million years in that area. And when I'm saying Lesser Himalayan duplex, that might not sound very familiar to all of you, but it is basically a structure that grows by basal accretion. So the downgoing plate here, the Indian plate, is accreting rocks not only at the front to the Himalaya, but also at the base. And when it's doing that at the base, there is a duplex growing, and it gives rise to this Lesser Himalayan anticline that often separates these north-dipping structures and strata of the Greater Himalaya from some clip-in structures farther to the south. Okay. Great. And so the idea, or the provenance data, tell us that these kind of rocks were likely exposed and eroding over the entire course of the material that is recorded in these fallen deposits. Okay, keeping time in sight. So what did he do? Now I'm going to present to you the 10 billion data, so the paleo-erosion rates. He went to the Haripur coal site, which exposes material that has been dated to between 6 and 1 million years, approximately. Stops at 1 million years or a little bit later, because that's the time when the MFT got active and uplifted these deposits and exposed them to erosion so that we could sample them, or Sanjay could. And he collected many, many samples and was able to retrace the former PaleoMax study, thanks also because he knows the people in Dehradun that were doing this, and was able to locate his samples in this PaleoMax. He also recalculated the age model using more modern techniques. And then spent a lot of weeks in the lab processing very large samples in order to get the concentrations, temperature concentrations out there. Now, before coming to the results, I want to remind you that when thinking about those samples, we envision that as the rocks are eroding in the source areas, so in the Himalayas, they start off at depth with a zero concentration. And then as they approach the surface, they acquire a signal, the one that we're interested in. So this concentration that they acquired just when they got eroded off the head slope. But then when they were deposited, transport is fast, so it doesn't really matter. And then when they get deposited in the foreland basin, they get buried. And this turns out to be the most complicated component, because it's not entirely clear how fast they get deposited. But it could be that some additional component gets added before they are deeply buried, and then they only decay. Well, not the samples, but the cosmogenic nuclides in the samples. And this is radioactive decay, well known, until a point that the structure gets active, exposes these deposits to erosion again, and Sanjay takes the sample. There might be an additional increase in concentration again due to recent exposure, but the good thing is that it's very small. Because, why? Because first, production rates are very low. It's close to the equator, it's very low in elevation, so it's really only a couple of atoms per gram per year. And the other thing is that uplift rates are very high. So we have very high uplift rates in the Schwaliks, And that makes this component relatively small. But he also, in his calculations, tried to take this into account. But what is also important, and what I want to point out, is that the production rate is important. The production rate of the source area. This is the term that we need to know in order to extract the paleo-erosion rate. And this is something that is tricky, and I will come back to that later. The second thing that I want to say is look at the stratigraphic column here. And you may note one thing which is surprising, is that as we go towards the top, so as this depositional site gets closer to the mountain front, the sediments that are fine-grained get more abundant, which is not really what we expect. We expect those things to get coarser, right? Conglomerates to come in. And there are indeed some conglomerates, but in between the conglomerates, a lot of muddy rocks, and also the sandstones here look different. And this actually, we think, is related to the fact that the source area likely changed for some of the deposits in this section. And why is that the case? Well, this can be seen here in these maps. So the yellow colors indicate the shibboleth sequences, with the upper faint yellow, the middle, and then the lower shibboleths not exposed here, but there. And there you have also the lower and the middle shibboleths exposed. And so these rocks here are actually fallen basin sediments that have been accreted more recently to this frontal part. This is just showing that this is the mega fan currently. Interesting, I guess. But more interesting is this Google Earth image. And here's the Haripur coal section. And these rocks, or these mountains, this belt of hills, I should rather say, these comprise the uplifted middle shibboleths and other rocks. So they were deposited before 5.3 million years. And note the Giri River, which comes down here and then gets deflected, probably by accretion of these slices here, and then gets further deflected, even flowing a little bit to the northwest. To the west. I have to, the image is rotated. So it flows a little bit to the west here. Oh no, not even west, it's east. Anyway, don't worry. Flows in this direction. And this is not natural. I think it is because the structures grew in this direction and deflected this river away. And that makes the Haripur coal section, it's currently exposed here, but in the past it was farther to the south, more inceptive for rivers that are coming off these hills here. And this is likely what we think the reason why we observe these mud rocks and so on. Unfortunately, it cannot be really detected by the geochemical methods, because you're recycling similar rocks that have been deposited in the fallen basin. Okay. I'm already 47 minutes on my cell phone, so I got to speed up a little bit because I still have quite a bit to tell you. Some impressions from taking his samples. Of one way he took samples, oftentimes at rock, places where the river is actively eroding and driving back the hill slope. So we believe that he did a great job in collecting as shielded as possible samples from these sites. Now here are the results. The 10 beryllium concentrations only, no erosion rates here in this figure so far. Sanjay also collected samples from these major rivers again, and also from some of these, steep rivers that are draining the middle shibboleth deposits that are uplifting, and measured the concentration to get an idea about what these concentrations are. And from these rivers, modern concentrations are here for these modern Piedmont samples, and the modern Yamuna samples here have concentrations up there. And if you just take their concentration and let it decay with time and compare it to the measured concentration, that we see that those samples here that we identified to belong to the Yamuna River, it's mostly here, but some in there as well, have a similar concentration. And then there are samples down here that have a lower concentration. It becomes a little bit tricky to separate here, but more evident here, that are very similar to the concentrations of the modern Piedmont samples. Now, if we calculate the paleo concentrations, this is what they look like. These are the paleo concentrations, indicating lower erosion rates up here, higher erosion rates down there. And if we now take the next step to calculate from the paleo concentrations, the paleo erosion rates, this is what we get. rhetoric break, maybe, to let it, yeah. Okay, so on the left-hand side, the Piedmont rivers. With those, it's a little bit tricky because they have relatively low concentrations. And if we subtract what we think might be the burial contribution, then some of them seem to get close to zero concentration, which is not possible, right? So it's a little bit tricky to really tell what's going on here. The best guess is probably that maybe the burial is we take too long burial into account. But it's hard to say how fast did it, how fast was it, right? So we stick to our burial model, which is based on some, observed rates of burial along the Himalaya at present, because we're interested in burial over the first, 5 or 10 meters or something. This is a point where the satellite effect comes into play. So it becomes really tricky. But whether we take a simple burial model, a more complicated one, the one that we're showing here, or take no burial time at all, so deeply buried, no more exposure, what remains is that the samples show a kind of a cyclic variation in erosion rates. If we do a periodogram, then the spectral analysis, we observe that there seems to be something between 0.7 to 1 million year or 1.1 or something cyclicity in there, which is evident from these, low, high, low, high, low, high, and so on. This is where the Piedmont rivers come from mostly here, and this is where the Yamuna River comes from. So first observation, cyclicity. Second, if we plot a trend line in there, it would be slightly increasing towards the present. And I want to, sorry, I'm 15 minutes already. If I need to, really speed up and make this talk end fast, then just jump in and tell me. Otherwise, I will just continue. Okay, so increasing trend, I try to explain our reasoning why we think it's related to tectonics and not climate. First argument is that we know that changes in monsoon intensity that are often cited to account for changes in erosion rates in the past. They occur on orbital timescales, so relatively high frequent compared to what we observe. So that's kind of ruled out. And the second, and this is a little bit of an embarrassing slide because I forgot to make it until just a few minutes ago. So, but I wanted to say is P up, Z down, or the other way around. So what it means is that over very long time scales, the point is that if you, let's say, change precipitation dramatically, then we would expect that erosion rates go down and an uplift continues and makes the topography steeper. And as it gets steeper, erosion rates increase again until erosion rates match uplift rate. So this is the conceptual model. But we don't have a step change. We have a very long wavelength, slow change over long time scales. In the Himalaya, because erosion rates are so fast, basically the topography would always be able to keep up with the changes. So you apply slow changes in precipitation, but the Himalaya, the rivers, can adjust gradually and change the topography such that erosion rates are on par, basically. So we think that this is not something that we expect. I also have a slide behind my conclusion slide. A slide behind my conclusions referring to the Nature Geoscience paper from the French people that shows the erosion rate, paleo-erosion rates based on 10 beryllium from the Bay of Bengal over the last 10 million years or something. And it's relatively not a lot of variations in there, so relatively flat. So it might also be considered support if you don't believe the argument that I'm bringing here. Anyway, erosional cyclicity. So what do we think? We think that it's related to episodic basal accretion at the base of the orogenic wedge, and that this leads to changes in uplift pattern and therefore in surface uplift because the topography takes time to adjust to this transience in the uplift pattern. But there's also a problem which is related to if the topography changes, it also changes the production rates. And we stick to one production rate in our calculations. So there might also be an apparent change in erosion rate that we cannot really account for. So that's the issue. The lower panel here shows you what other people, including us and so on, think of how the Himalaya has grown with time. This here is the Lesser Himalayan duplex, which has grown over the last maybe 10 million years or so by episodic accretion of thrust slices or horses, as tectonic people say, to the base of the belt. And this means that the current MHT, as it is, gets abandoned here in this part. The ramp gets abandoned and becomes a flat portion, indicated here by the stippled line, and a new ramp grows there. And then this thing gets accreted. So remember, the ramp is where uplift rates are high, and that jumps basically down south to the front, towards the front, and then it gets sucked in with subduction further to the north until it reaches a point that, again, it jumps to the north. And this is kind of an episodic process that again and again creates this basal accretion, which we link with the erosional cyclicity that we observe. To make this point, or there's one thing we can do. We can look at these, we cannot look at these thrust slices because they're at depth, but we can, make informed guesses, let's say. And what we did here is to look at balanced cross sections across the Himalaya. And even though those people that constructed them could also not, look at depth and see how long these thrust slices or horses are, they invested a lot of time, field observations and other things in order to make a best guess. And so what we did is just to measure the length of these thrust slices in the Lesser Himalaya. And this is what we get. The length of these thrust sheets or slices has a distribution. Some think they are very long, some think they are more short, depends on location and this and that. But if we just take an average guess of something like between 15 and 37 kilometers length for a thrust sheet, and then we take into account the shortening rate of approximately 16 millimeters per year at this place, then we obtained a periodicity of about 0.9 to 2.3 millimeters. What we observe in the erosional periodicity is something between 0.7 and 1.5 millimeters. So it seems consistent, at least, that these numbers are not like unreasonable. Next thing I want to bring is to show to you the landscape evolution model experiment, which we set up in the process of getting this paper published and satisfying reviewer comments, in which we, very simple, have this landscape here. I'm just going to run it while I'm talking. That's probably the best thing. How? This way. So we have this block uplifting and running into steady state, basically, at a constant rate. And then at some point, there is a zone of more rapid rock uplift. And this is basically our MHT. And we're looking at this window of the landscape and assume that this MHT, so the ramp, moves back as the subduction continues. And then at some point, it jumps to the front again. And then it goes back and jumps to the front and so on. And so this cyclic behavior that we're simulating here is shown here in terms of elevation, as most of you have guessed already. I guess some rivers are shown in there as well. And these red squares indicate nick points that are migrating through the landscape. And so this kind of behavior then leads to this sort of variation in mean elevation and also in mean production rate. And we've chosen here a frequency of 2 million years because this basically showed it nicer as compared to something shorter. But I want to emphasize that I wouldn't, put too much, emphasis on the exact values that we get out of this, or the frequency and all that, because there's a multitude of parameters that control it. But the pattern is important. And what is also important is that in the model, we can now track production rates. We can track the topography, how it changes, and correct for the effect of the production rates. So what you observe here is now the Temporal concentration that we would expect to get out of such a cyclic behavior. This is the erosion rate that is actually occurring because we have a model, so we can really track it. And this is the erosion rate here, the stippled line, that we would expect if we measure the Temporal concentration and assume a constant production rate. So part of what we observe in the erosion rate changes, we think, is due to a false assumption about constant Temporal production rates. But we have no way of doing better, no way of correcting for that. So I think it's good, to keep it in mind, but it means that not the entire cyclicity, I would say, is related to this this basal accretion. Now, close to 1 hour, bear with me, 5 more minutes or so, and then I'm done. The increasing trend, which is this one here, what is that related to? Well, this is also, it has to do again with all these structures and how they play out in the shape of the origin. Remember, the main Himalayan thrust, the ramp, is basically all the origin of the high Himalaya. And this is oftentimes also the boundary of the catchments that flow to the south. So it's like a ridge line and a barrier for rainfall, and it basically the Yamuna catchment terminates at these high points. And then the southern termination of the Yamuna catchment has been for a long time the MBT. So this is a structure that has been active prior to the main frontal thrust. But while we had accretion occurring here, and frequently, there was no frontal accretion really occurring here. Some a little bit farther to the west, but in the Dehradun area, not much at all. So only about 1.5 million to 1 million years ago, the MFT got active. But prior to that, it was the MBT. So to make the point clear, this is an analog model by the authors down here with a sand wedge. And what they did is to have a layer with glass beads in between so that the upper part of this incoming layer gets accreted frontally, but the lower part gets sucked in and then accretes basally at the base here, because this is a backstop where no more material gets subducted. So this is underplating or basal accretion. This is frontal accretion. In this case, it's really frequent. You have basal accretion, frontal accretion, basal, frontal, or simultaneously or whatever, but both are relatively frequent. And the relative frequency of frontal and basal accretion in the Himalaya is not equal through time. Instead, we have currently the MFT be the most southern frontal thrust. And this was activated about 0.5 to 1 million years ago. Before that, it was the MBT, it's here. And then before the MBT, I don't know. I think it might have been the MCT or some other structure beneath the MCT, but the MBT must have been a structure that was active for a long, long time. At the same time, we have basal accretion and duplex formation back there. And because of this unequal frequency, we think that with time, the Yamuna catchment has always been extending probably to where the ramp is. The ramp where there's high uplift, high mountains. This is the northern end of the Yamuna catchment. And the southern end has been the MBT for a long time. And with time, the Yamuna catchment shrunk in size. So it got shorter and the wedge probably got steeper. And so for that reason, we think that the same accretionary flux over the timescale we're interested in, or distributed over a shorter or smaller basin, is accommodated by higher erosion rates. And this is reflected in this increasing trend. More recently, there was frontal accretion extending the belt again, and now the cards are shuffled again, if you want, with changes. But this is our sort of like hypothesis. I would like to say. I want to put out there for people to discuss. Okay, conclusions. My main conclusions: what controls the magnitude and distribution of erosion? We think, and I think it's mostly tectonics, at least in Gawal. Do erosion rates vary along with climatic changes, and if so, by how much? It appears that precipitation influence is small, relatively small. Note the time scale for those climate skeptics. Temperature influence through glaciers still exists. I mean, glaciers erode deeper, and we see that in long profiles. So there must have been an increase in erosion through glaciers. With frost as well, yeah, perhaps. Why not? This is something we need to dig deeper into. How stable and variable are erosion rates in the long term? Well, we observe relatively variable erosion rates, even though some of this is, apparent, I would say. But there seems to be an erosional cyclicity apparent that we relate to the tectonic accretion that is ongoing in the Himalaya there. And I also have a thank you down there, but before, this is a recorded talk. So here is a slide with references. I move the pointer out because when you look at the talk later on, you can make pause now and look at the references. I go back to the conclusions. I want to thank you for your attention and allowing me to speak for a little bit more than 1 hour. Sorry.
Thank you so much, Dirk, for this very interesting talk. And I also want to thank you for making it so accessible for a broad audience. I think you really did a good job in explaining also some of the basic things that not everyone are familiar with. So well done.
Thank you.
And we've opened the chat for questions and comments. So everyone feel free to add something in there. You can also, as I said before, raise your hand. You do that, as far as I remember, in the reactions, but with the reactions button. But while we wait, perhaps I can ask a question myself about this erosion burial model you're using. I mean, to me, there seems to be quite a number of parameters there that may be more or less constrained. What do you do to sort of explore the uncertainties on these different, for instance, what happens in the catchment before burial?
Okay, I think I sense two questions. So what happens in the catchment? I mean, we've seen that from the second study, basically, that I was presenting, that material gets deposited in valley fills and then gets eroded, but the time scale is short and there's not that much going on during this time. Even if it is exposed for something like 50,000 years, it doesn't do much to the concentration in terms of decay. The only thing that it does is to this upper thin layer, there will be an increase in concentration over this time scale, but the total amount of material, relative amounts, this thin layer is tiny. It's very small. So we did some calculations in this 2015 paper, which suggests that it's not really an issue. Now, when you address this burial part, this is where it gets deposited in the foreland, it gets buried. And in the paper of Sanjay, we basically looked at different burial scenarios. So what happens if it's instantaneously buried, if it's buried at the rate that is the mean rate of the paleo-max section, or at local rates of the paleo-max section, and so on. So we did all sorts of things, but the cyclicity remains. And my best guess is that it really gets buried quite quickly. This is also because of the Piedmont rivers. When we do the burial correction, like if we allow for long burial times, then we get negative concentrations, which does not make sense. So there needs to be something shorter, and I think, and the shorter it gets, the more so the cyclicity remains. That's basically the main point. I hope that answers the question.
Yes, thank you.
Okay, should I read out the first question?
Yes.
The first question from the chat is from Ed Rhodes, asking about the second half of your talk. Do you think there's the possibility to find locations where a similar process is occurring between frontal and basal accretion, but with a different frequency owing to differences in fault geometry? That might be a good way to demonstrate the validity of the model.
Absolutely. Hi, Ed. Yeah, thanks. I totally agree. And I mean, obviously, probably somewhere else along the Himalaya would be the first place to look at. And also other places on the planet, wherever that might be possible. I guess the important things that need to be considered is like, keep the catchment as simple as possible. So the Yamuna is, in that sense, even if it was glaciated, it wasn't super heavily glaciated. It doesn't matter for the record that we're looking at, because that was only from 6 to 4. But if you have something over the last 2.5 million years, you want to be concerned about that. The other thing is, if there are sort of like captures occurring during that time, that might also be problematic. So there is a bunch of things, or there are a bunch of things that could be problematic. I think in our scenario here, in our setting, we're pretty safe for most of those. And both the frequency of the process as well as the sensitivity of the system, like with the erosion rates, that also that they are relatively high and they should track whatever change you apply. That's all, plays out in favor for this place. And I would probably go to the Himalaya elsewhere in the first place, but be prepared to spend a long time in the lab working on really dirty samples. I think Sanjay had to dissolve something like 100, 150 grams of quartz in order to get enough concentrations out there per sample.
Okay, so I will move on to the next question from David Kelly, who is curious about the effects, if any, of changing sea levels on erosion rates and terrace formation in the system you'd studied. Presumably, base levels of streams affected these rates as well.
Yes, but the coast is far away, so it doesn't matter. I mean, if that's, sorry, a short answer, but currently the coast is in Bangladesh, somewhere there, and we're something like 300, 400 meters higher at the outlet of the Yamuna or so. And during interglacial times, sea level variations were not big. And we know from the over the time scale that we are observing, I don't think that there's any sign of marine deposition in the Fallen Basin that higher up. I don't know what it's close to the delta, but yeah. So I don't think we have to be concerned. I hope that is a reasonable answer to that question.
Okay, we have another question from Rajashi, and he says, my question is rather generic. Catchment-wide denudation rates are routinely reported using cosmogenic nuclides in areas where bedrock is exposed. And you mentioned that an average rate can be obtained from river sediments. However, what about unusual substrata like laterite, specifically lateritic gullies catchments? In lateritic areas, bedrock is commonly not exposed easily, and there is down profile leaching of silicate. So my questions are, one, do you need to sample both river sediments and sediments from up-catchment parts? And two, which cosmogenic isotopes would be ideal if silica is being lost out?
I think this question is would require, like, get a full answer would require a little long time, but there are a lot of papers that discuss this. In general, there's also a really nice paper by Daryl Granger and Reby, where they look at their websites what it is. I think there was two versions, 2007 and 2014, overview paper, cosmogenic nuclides in studies of erosion and weathering or so, and they go through these different sites where you can apply this the method, including bedrock, but also then mixed soil that is mixed, and then catchments and so on and so on. Overall, in general, I would say, like, there's always a way to apply things. Beryllium is good in anything that is quartz bearing. When you come to more complex minerals and lack quartz, then you can think of other elements. Usually there are solutions, and if there are none, then it might be worth sort of like thinking about whether, developing the method further. But I think, it becomes a little bit tricky to answer all these detailed things.
Okay, then we might just move to the next question by Nadia Insel.
Mm-hmm.
Your paleo-erosion rates decrease if you take glaciation at high elevations into account, but they are still higher than recent erosion rates. Does the deglaciation at these elevations increase landslide occurrences that could count for the higher paleo-erosion rates?
Yeah, perhaps. It's a good question. It could happen that, we do see some variations, right? And the problem in this, over this time scale, is also that we don't exactly know how extensive the glaciers were. The oldest glacial deposits that I was able to date in the Toads Valley, I think, were I can't recall, but let it be, now that production rates have changed ever since that publication, a little less than 20,000 years. So all that we could say at that time, or with that publication, is that we have indication that glaciers is extended to there. So we grow them at least to there. Now, if they were exactly at that point, or farther, or less, or something prior to the most extensive glaciation in the Tones, is difficult to say. But I would, in that sense, probably assume that there might be some dynamics in, when these glaciers grow and then they shrink, that shrinking glaciers accompanied by landsliding and so on. So this could contribute somewhat to the wiggles we observe over this time span of 15,000 years, but it's really not so easy to tell. And another thing that is sometimes a little bit discerning is that if glaciers recede and leave behind a cirque or a cirque lake, then the cirque lake may account or may act as a buffer for sediments that are coming from higher up, and they are trapped in there for some amount of time until the lake is full and then toppled over. So these problems are difficult to really track precisely, I think. But this is a good idea, yeah.
Yeah, I actually would have a follow-up question or a related question to this. So you were showing that paleo-erosion erosion rates are still a little higher when you correct for glacial cover, but a lot less than we initially thought. But then at the same time, by just showing these massive alluvial fills, apparently the situation has changed through time. So what do you think actually causes these events of sediment deposition and later incision? Is it mainly changes in water discharge, or is like this little bit in erosion rate enough to actually fill the valleys?
No, I think actually in this case that it's changes in discharge. And also probably that where we observe the sediments, this is where erosion rates get really low, and then farther to the south they increase a little bit again. And you also see that in the landscape, gets narrower. So it seems that there might also be a lot, more opportunities to store the sediments. And I think that in this case, because in that 2015 paper, I think I compiled observations also from other places around there, around the Gawal Himalaya and elsewhere, and that a lot of luminescence ages, and they all indicate that there was widespread aggradation in the area during the Pleistocene, and then with the onset of the Holocene, these valley fills started to incise. The Pleistocene was a time when the monsoon intensity was low. There might be more sediment supply from glaciers affecting rivers, but at the same time, discharge was much reduced. And so I think that this would mostly apply. But as you know, Steffi, there are also other causes, and I wouldn't extend to any place in the Himalaya or on Earth. For example, my colleague and friend Wolfgang Schwanghardt, in his science paper from a few years ago, they observed this thick valley fill which originated from a massive landslide upstream in the, Kali Gandaki or so.
Great. Okay, thank you, Dirk. I think we managed to go through the questions in the chat now, and I don't see any raised hands. So perhaps this is a good time to wrap up for today. And thank you so much again for this really interesting talk.
Well, I thank you and all the people attending.
Good. And yes, thank you everyone for showing up. And if you meet somebody that couldn't attend, remind them that they can see it online. Afterwards, we'll put it on our website. Thank you, and see you again next week.
Bye-bye.